LIFE, the Laboratory for International Fuzzy Engineering Research, is a leading research center in pursuit of human-friendly technology. We believe technologies should be human-friendly. In other words, machines should understand the fuzzy logic behind people's words and actions. They should think just like humans do and act in harmony with us. The basic concept of conventional technologies is to analyze subjects with precision and draw out logic with objective accuracy. But this does not take into account the fuzzy and qualitative elements of human thoughts. This is why conventional technologies have failed to achieve human friendliness. Fuzzy engineering, on the other hand, can exploit ambiguous and qualitative concepts and knowledge and draw deductions from diverse information. This means that the technology examines a complex task from a wide perspective and summarizes its essential substance qualitatively. It can respond flexibly to slight changes in task content and the environment, or even utilize a person's subjective perspectives and experiences as new rules. Fuzzy engineering is indeed the answer to human-friendly technology. LIFE was set up in cooperation with industries, the government, and universities. In 1989, it launched a 6-year research program into fuzzy engineering. The development of fuzzy engineering can be divided into 4 stages. The first stage is to establish a fuzzy control system by giving machines relatively basic knowledge on human logic. By the end of the first 3 years, we managed to reach the second stage, where the system acquired more sophisticated knowledge, including qualitative theory and complex contradictory concepts. In the following 3 years, we explored the third stage, in which humans and machines exchange information freely and handle the same task in coordination with each other. To achieve such mutual communications and upgrade the intelligence and flexibility of machines, we launched 5 projects. This video is the record of our efforts in the third stage. In the Fuzzy Computing Project, our study focused on capturing the fuzziness of natural speech patterns so as to create a highly intelligent system capable of comprehending human logic.
じゃあ次ね。これ？いいよ。じゃあ if a person is killed, the person dies.
Okay. I understood. If a person is killed, the person dies.
This man is communicating with FLINS, the fuzzy lingual system, on a home computer system. A home computer can be used to support everyday life. For example, it can tell the user how to use an appliance and offer advice on various matters. The point of the project is to get a computer to use the theory of deduction to understand the meanings of ambiguous or figurative expressions in daily conversations. At the core of the system is a 3-stage processor for reasoning under ambiguity. The middle stage handles ambiguous phrases such as tall, almost, and certain. The upper stage processes proverbs and other expressions that have greater ambiguity. This 3-stage process enables computers to converse naturally with people. Vague adjectives and adverbs are classified before processing.
How should I grow up, Utah?
The system can deal with proverbs as well.
I got an answer. You should make him study hard because they say that we should strike the iron while it is hot.
For instance, the system used the proverb, strike while the iron is hot in this case, to answer the question, how can I help Yuta to grow up? The capacity to analyze vague speech patterns can be applied to the development of a mechanical control system. One such example is a system called FATE, which controls the gear shifting of cars with automatic transmissions. FATE is constructed with data written in fuzzy logic similar to natural speech. Based on this data, the system deduces the intention of the driver through his or her actions and changes gears automatically. More specifically, at first the system examines the car's speed and the angle of the accelerator and checks the current location through GPS, the global positioning system. It then analyzes road conditions and past road performance of the driver before judging the driver's intention and deciding on the optimum gear shift. We also developed a special computer environment, Finest, to make the compilation of such systems easier. Finest classifies the knowledge blocks and stacks them up just like toy blocks to compile a system. It analyzes ambiguous information through forward or backward deduction while displaying the process graphically. The tool can do a self-tune-up to boost its ability to classify ambiguous data when samples of typical input and output interaction are fed in. Another pillar of LIFE's research is the development of an intelligent interface which can interact freely with people and help their decision-making process. The system must be able to conduct coordinated and natural communication with humans. Based on this concept, we developed two systems, an intelligent database retrieval system and a cooperative dialogue system. In the course of a dialogue, people unconsciously summarize a massive amount of data with words. We successfully developed a way to artificially reproduce the process using artificial intelligence and genetic algorithms. The method is applied in the Intelligent Database Retrieval System. Conventional retrieval systems do no more than output the search results of a database. But this system converts data into linguistic information through a summarization algorithm and retains it as new knowledge. Even if a large amount of data matches the user's search conditions, the system can summarize all the information into a simple statement.
Apartments are retrieved. Most apartments are classified as follows. Which apartment do you want best?
When there is no applicable data, it offers other types of related data, rather than just say, no matching data available. An increasing number of networks offer database services accessible through portable computer terminals. This type of data summarization and compression will be essential to save on data transmission time. Next, let's take a look at the dialogue system, which allows users to interact with machines verbally. This system comprises the dialogue management subsystem, the decision support subsystem, and the user model subsystem, which governs information about users. The main feature of the system is its capacity to offer individual replies to each user. At the onset of a dialogue, users have yet to clearly define their needs and tend to use many abstract expressions. This system grasps the topic by filtering the information through individual membership formulas. It also paraphrases its questions so that the user can reply easily. It clarifies the user's needs through such dialogues and aids in their decision-making. This is one example of its friendly interface. The friendly interface is also seen in the choice of dialogues. Rather than offering direct responses to questions or demands, the system adds extra elements that may be useful to the user. Fuzzy technology helps machines understand and use language accurately. For the first time, humans have acquired a friendly and natural interface with machines. In conversation, gestures and facial expressions are important elements. The Fuzzy Associative Memory System, or FAM, was developed with the technologies of fuzzy logic and neural networking to support a multimodal interface capable of recognizing gestures and languages. This system, now under development, analyzes the movement of a tennis player and issues verbal advice. FAM deduces macroscopic judgments by the player and refines its knowledge on tennis movement. Based on three-dimensional images, the system compares each movement with a pre-recorded model performance and analyzes its meaning. Then it selects the most appropriate advice among past instruction examples and feeds it back to the player vocally. This system also understands instructions given by gestures and words and reproduces the movement visually. Users can use macroscopic judgment and instructions to interact with the system. The multimodal interface is expected to be applied in a wide range of areas in the future. Among some examples are the partial modification of facial expressions to enhance communication and the development of an automatic translation device for sign language. Another project to create a human-friendly interface is the development of a two-way conversion of image and verbal information. In studying the conversion of images into language, LIFE has explored the Gestalt theories of perception, according to which perception is based on the organization of input signals. Principles of grouping and discriminating these signals are also given. In our study, the signals are actually straight-line segments fitted to the results of edge detection. Grouping properties such as similarity, proximity, closure, and continuity are defined and used to infer higher-level structures, longer straight-line segments, straight and curvilinear junctions. Fuzzy modeling can be used to learn a suitable representation of perceptual organization rules. In fuzzy perceptual organization, emphasis is on structure inference, which differs fundamentally from other perceptual organization methods. Our researchers are also trying to develop a method of modeling three-dimensional shapes from a sectional view. Here, other researchers are developing a method for perceiving objects from their colors. Among other results is the object location system. Using pre-recorded maps, the system locates a target object from two-dimensional images.
Where is the clock?
A clock is around the center on the wall.
Where is the computer?
A computer is slightly right from the center.
This technology has brought about the development of a voice system which informs users of the locations of objects surrounding them.
Where is the cabinet?
Something like a cabinet is slightly left from the center on the floor.
The AI language Frill is used to program an intelligent fuzzy data browser. This system can answer any relevant query of a database. Mass assignment theory is used to automatically form a hierarchical set of fuzzy or evidential logic rules from which the required generalization can be obtained. The rules can be tested, and the user can interact with the system to suggest changes and understand the nature of the rules. In this work, image generation from linguistic expressions is studied. Due to the recent remarkable progress in computer graphics technology, easy designing tools for 3D object models are desired. Linguistic input can be a solution to the problem. To accept the fuzziness of linguistic expressions, a model consists of global shape information and size parameters described by fuzzy sets. According to the linguistic input, the system generates a 3D model. Visualizes the generated model and shows the created image to the user. This system enables users to deform the shape of objects and to generate new 3D models. On the other hand, by adding a matching process with real images, this study can be applied to the area of object recognition and the development of a design support system. The Intelligent Robot Project aims at establishing a basic technology for developing a robot system that can coexist with humans in harmony. The system comprises 4 elements. The first element is the inference of human intention from actions. The second is planning to handle ambiguous concepts appropriately. The third is the cooperation rule, so so robots can perform tasks efficiently and in coordination. The fourth is reinforced learning capacity. In this project, researchers are trying to give a robot the ability to infer human intentions from their actions in order to decide on its next actions accordingly. Here, a robot is predicting the actions of another robot, which is representing a human. Fuzzy logic is the most effective way of deducing human intentions. To carry out a task which is not pre-designed, the system must have a planning capacity to arrange and use knowledge found in a database. LIFE developed a general use planner capable of handling ambiguous data. For example, when performing a string of tasks, people tend to issue ambiguous instructions to a robot with words and gestures. When a person tells a robot to put the yellow chair on the right at the back, it classifies the instruction into fuzzy information groupings and draws up a satisfactory and effective plan for execution. Exactly the same instruction could point to a different location, depending on the circumstances. The robots share a common algorithm. That means they can work in coordination while mutually avoiding operational troubles and carry out plans to fulfill their purpose. LIFE also developed a high-speed enhanced learning algorithm, which gives the robots the autonomy to make their own judgments. Robots with this system assess their environment, decide what action to take, and move as they program themselves automatically. They learn the way to the goal through trial and error. LIFE has also conducted other research to increase the effects of other studies. One such example is the study on macroscopic judgment and strategy making of a Japanese board game called Go. On the Go board, black and white stones make patterns representing concepts such as strength, width, and thickness. The pattern changes every time a new stone is placed. The aim of this project is to enable a computer to read the qualitative changes of the board patterns, find the focus of the game, and devise a strategy. The strength, width, and thickness of the patterns are expressed in language rules, which serve as a base for situation evaluation. Once the evaluation is made, the focus of the game is identified in accordance with fuzzy rules to judge its next responses to set a trend. A helicopter has a wide variety of flight modes, such as hovering and reversing. However, it is most noted for operational difficulties, instability, for being easily affected by the environment, as well as for complicated operation procedures. By contrast, anyone can operate this intelligent unmanned helicopter from the ground, issuing commands in simple everyday language. This helicopter's control system is governed by hierarchical fuzzy logic. qualitative commands are filtered through a command interpreter to be sent to the section controlling aviation modes. This section operates 4 controllers in different combinations to follow the commands. Upon receiving a command for thrust from the upper hierarchies, controllers in the lower hierarchies follow if-then style fuzzy reasoning to determine the thrust. The helicopter also finds its own position with the help of GPS. And searches for a landing spot using the image guidance control system built with fuzzy engineering. It has enhanced operational autonomy.
The definition of our understanding is interpretation between machine and human.
A human-friendly system has to allow people to operate it through plain thoughts and dialogue. Free communication between humans and machines is the theme of the 3rd stage in the development of fuzzy engineering. Through our research, we have become firmly convinced that fuzzy logic is the best tool to create a system in which humans and machines can perform cooperative tasks. This stage and the coming 4th stage will pave the way for the development of a highly integrated artificial intelligence system. The 21st century will literally be the age of fuzzy engineering.